Hello everyone, my name is Guangmeng Zhou from Tsinghua University. I'm glad to have this opportunity to present our work on efficient design of intelligent network data plane. As we all know, AI experiences increasingly popularity in networks such as adaptive bitrate, congestion control, and routing. AI models are often deployed to work on the end hosts of network control plane. In contrast, deploying the learned models on the network data plane for traffic analysis is a relatively less charted area. Such a capability, we call the intelligent data plane, may transform a lot of network designs, such as malicious traffic detection, the ECN threshold adjustment. However, IDP is nearly impossible using traditional switch chips because they are specialized and protocol-defined ASIC architecture. Fortunately, programmable switches have potential to enable IDP. It's based on the protocol-independent switch architecture. The programmable switches have two pretty cool features. It supports customizable packet processing and stateful storage, but it also has some constraints, including computation constraints and storage constraints. These constraints aim to ensure high-speed traffic forwarding and pose many challenges for deploying intelligent models. We classify prior traffic analysis art on programmable switches into three classes. The first class, such as flow length, collects information on the data plane and do traffic classification on the control plane. Due to the interaction latency between the data plane and the control plane, traffic is not analyzed at line speed. The second class, such as Poseidon, both collects information and do traffic classification on the data plane, but classification logic is based on threshold-driven traffic filters, not generalizable to the complicated use cases. The third class, such as Mosca, considers per packet features and deploy decision tree model to do the classification. However, they have low efficiency in representing learning models. More importantly, traffic is not analyzed at the flow level, which is necessary for traffic analysis. Thus, we design NetBeacon to advance the state-of-the-art by simultaneously achieving line speed, learning-based, and flow-aware traffic analysis on the network data plane. I will start with the structure of NetBeacon. NetBeacon is designed around two major questions. The first is how to get hardware-friendly learning models, which includes feature engineering and a multi-phase sequential model. The second question is how to deploy models efficiently, which includes model representation and stateful storage management. Model representation transforms the model to flow table in the data plane, and the stateful storage management addresses the limited data plane storage resources. The above designs constitute the overall NetBeacon. When packet arrives in the data plane of switch, it will go through flow identification, updating the storage, calculate features, query tables to do traffic classification, and finally be processed based on the flow class. Next, we elaborate on each design. In the feature engineering, we select features which are extractable or computable on the pipeline, include the packet level and flow level features. In the model design, we stick to decision tree models because their constructions are more similar to the match action operations on the data plane. We observe that flow level features are dynamic as a flow process. For example, the variance of the packet size when 4 packets are received will differ greatly from the variance when 16 packets are received. Thus, we design a multi-phase model architecture to apply different models at different phases of flows. Then, we transform the model into flow table in the data plane efficiently. I will introduce the model representation with a simple tree model. There are 3 features and 6 leaf nodes in the tree. The leaf nodes represent the classification results, and a path from the root node to a leaf node represents the matching rules for that leaf node. Thus, we can transform the tree to table 1. The keys in table 1 are ranges. However, range matching is not universally supported on programmable switches, and it has to be coded into ternary matching. Thus, we have table 2. Unfortunately, it has combinatorial explosion of entries. For example, one entry in table 1 needs 8 times 1 times 6. That's 48 entries to represent. The straightforward solution to the explosion of entries is that each range is represented by one ternary string. Thus, we propose the range marking. In this way, we represent the model with multiple feature tables and one model table, where the feature table matches features to range marks, and the model table matches range marks to classification results. Each leaf node only consumes a single ternary entry in the model table. The details can be found in the paper. However, the keys in the feature table are still ranges. Note that the ranges to be coded in each feature table are consecutive and cover all possible values of the feature. Based on this characteristic, we propose the consecutive range coding (CRC) algorithm to reduce the number of table entries in the feature table. For example, the number of table entries representing the range 65 to 103 is reduced from 8 to 3. Finally, the tree is transformed like this. Meanwhile, we also design how to represent different forest models based on a single tree. The details of CRC algorithm and handling forest models can be found in the paper. Stateful storage in programmable switches helps us to save flow information in order to use flow-level features. Each set of registers holds the information of one flow, which stores the flow ID, class, and other required information. The register index is the flow hash. Because the stateful storage is limited, the index collisions are common. Once a storage collision occurs, the per-flow states of both the original and the new flows will become dirty if the new flow overrides the storage. Therefore, we propose two designs to mitigate this problem. Considering that most packets in the network are from long flows, we maintain flow information only from long flows and use packet-level features for short flows, which reduce the overall chance of collision. NetBeacon introduced a long-short flow binary classification model using only per-packet features to decide whether a packet belongs to a long flow or not. When the storage collision happens, NetBeacon allows the new flow to use the occupied register if the inference class of the old flow is determined or the old flow is finished. Combined with the above designs, our integrated data plane processing logic is shown in the slide. A detailed description is in the paper. We implement a prototype of NetBeacon on Barefoot Type 1 programmable switch and connect the programmable switch to Linux servers. We use packet-level macro accuracy and data plane table entries as the metrics, and evaluate on the three tasks: that's P2P application fingerprinting, carve-out channel detection, DDoS attack detection. The baseline is Mosca and the variants of NetBeacon. In the experiments compared to Mosca, NetBeacon has a significant accuracy improvement. That's 15% in P2P application fingerprinting, 38% in carve-out channel detection, and 20% in DDoS attack detection. Compared with the ideal case, where we can allocate stateful storage to all flows, NetBeacon achieves comparable performance. Then we show that the data plane model representation of NetBeacon is more efficient compared with other IDP works. The evaluation metrics are the classification accuracy and the number of data plane table entries required to represent the model. In the four tasks, NetBeacon achieves higher accuracies when consuming the same number of table entries, and uses much fewer table entries when representing similarly performing models. Here we explore the factors affecting NetBeacon performance. In the first figure, the accuracy of earlier phase is relatively low, which means the flow level information could be premature at earlier phases, and the accuracy increases as more inference phases are appended. In the second figure, the accuracy increases as the storage size increases, which means the storage size is important for traffic analysis, and the stateful management optimization of NetBeacon is useful upon the limited storage. Finally, let's conclude this work. In this work, we propose an efficient IDP design which outperforms prior art in both learning model accuracy and model representation efficiency. It has three major designs: data plane-aware model, efficient model representation, and stateful storage management. This is our source code address and my email address. Thanks for listening.